Okay, we have a question here. It says the particle is thrown upwards from ground. It experiences a constant resistance force which produces a retardation of 2 meter per second square. That means clear, it will be opposite to it. That means in this direction there is already G is acting in this direction, and in addition to that there is another retardation which is there, that is 2 meter per second square. That is, this is another A. Let's say it is moving up with a velocity u, and finally it will reach at a velocity which is equal to 0. It will stop here itself. If the final velocity is stopped here, let me say it has reached a height of h. So let me calculate it. So the time of ascent, which I shall be calling as time of ascent, I'll be calling as a TA. I'm just here to calculate here TA. Here to calculate TA, I'll put the formula b equal to u plus at, b equal to u plus at, and the final velocity is 0. So automatically time of ascent TA becomes this u upon g plus a. This is my time of ascent in this case. And what about h? And let's calculate h. How to calculate h? That means I'll utilize the formula s equal to ut plus half at square. In this case, s is h and u is u, and time I already know, that is u upon g plus a. And anyway, this is in the opposite direction, so I can put it in that way. This is minus half into g plus a into t square, that is again u square upon g plus a whole square. Fine enough. So this h is coming forward as h is equal to u square upon g plus a minus u square upon 2 whole into g plus a. If this is the condition, then I can tell you h is equal to u square upon 2 whole into g plus a is my final h, the height which is reached by the ball with this velocity, and given the acceleration is equal to in the opposite direction g plus a. Right now the question is of descent. I call this as time of ascent, and I'll call this as time of descent. During the time of descent, you can see the initial velocity during the downward travel is equal to 0, because this has already stopped here. Now it will try to descend from this particular point, and here u equal to 0, and we are already at a height of h. If we are already at a height of h, and this will descend in this direction, and we have a gravity which is always acting downward, but in this case the retardation which is there is acting in opposite to it. That means it's going to be g minus a. If this is the condition, let me just put it into the equations. That is, I'll put the same s equal to ut plus half at square equation. Then s becomes h and u 0, so I'll put it as half into this is g minus a. Both are negative, so h is negative, g minus a is negative, so I'm not putting it up forward. G minus a into time of descent square. If you look at it, this is time of descent square is equal to 2 upon g minus a into h. What is h? This is u square upon 2 whole into g plus a. If this is the condition, you look at it carefully. So time of descent becomes root over of this 2 cancels 2. This is root over of u upon g plus a into g minus a under root. This is my TD, that is time of descent. Now I have a situation here. I'll be putting it as into, I'll put the ratio now. Look at the ratio. If I say this is time of ascent upon time of descent, look at it. This is u upon g plus a divided by time of descent, which is this. So it will be multiplied in the opposite manner. That is root over of g plus a into root over of g minus a divided by u. Anyway, u cancels, so there is no point of the initial velocity. So the ratio becomes T upon Td is equal to Root over of g plus a will cancel here, and this is gonna be equal to root over of g minus a upon root over of g plus a. That is equal to g minus a is 8 and g plus a equal to 12. This is 2, right? So 10 minus 2 equal to 8 and 8 upon 12 root over. That is equal to, you can say 2 upon 3 root over, that is root over 2 upon 3. That's absolutely right. This is the answer. But here is a question.